Hi, so this is the third video in which I explain MDL. In the previous two videos, I first introduced what MDL was. So MDL is a little project I'm working on with the goal of optimizing assembler code. In the second video, I talked to you about the different types of assembler input and that MDL can take. And in this video, I wanted to talk to you about the actual optimizer. How does MDL actually optimize code, right? So as I said also in previous videos, MDL is in its early stages, so I have only been working on it for a few weeks, I think 2 months right now. So in my plan, I want to have 3 different optimizers inside of MDL: a pattern-based optimizer, a register allocation optimizer, and then a full-fledged search-based optimizer. But in the current version, only the first one is implemented, right? Like the pattern-based optimizer, which is a very, very simple optimizer, which is the one I'm going to talk to you about today. It is quite simple, but it is already interesting enough. So it already generates quite a lot of optimizations. So how does it work? So a pattern-based optimizer works by having a manually defined set of optimization patterns, and I will show you examples of those patterns just in a minute. Now, if one of those patterns matches some part of the source code, an optimization is triggered. Right? So this type of optimizer is also known as a peephole optimization or peephole optimizer. And for example, the SDCC C compiler actually uses a peephole optimizer. Right? So this is not, MDL is not the only peephole optimizer for Z80 code. All right, so let me just show you an example. So why do I mean by an optimization pattern? So this is an example pattern included in MDL, right? So in a pattern we have this first part. So there's 3 parts in a pattern. There's a pattern, a replacement, and then constraints. So the first pattern is a set of partially specified assembler lines. And if we find any piece of the assembler code that actually matches with this, that means that we can replace it with this if a set of constraints is satisfied, right? So if this appears in the source code and these constraints are satisfied, that means that we can safely replace it with this, and that will constitute an optimization, right? Let me just show you with an example. Imagine we have this little piece of code, right? It's just a function that loads some memory value into A, increments A, and then stores the value back into the memory, and then it does something else, right? So let's see. So could we apply this pattern here? So the first thing is to see if there is any part of this code that matches with the pattern. And there actually is. So these 3 lines correspond to exactly these 3 lines. If this variable const is equal to variable, right? And this variable op is equal to inc. If const is equal to variable and op is equal to inc, this pattern is identical to this code, right? So we have a match. So once we have a match, the next thing we have to check is whether these constraints are satisfied, right? So the first constraint says that op has to be either an inc or a dec. So op is inc, so this constraint is satisfied. And the second constraint says that the register A and HL do not have to be used, so their value cannot be used after the instruction number 2, right? So we can look at the code and we can see, let's see if A is used, right, the value of A. The value of A is not used because just here we are overwriting A, so whatever the value that A had here is not used. How about HL? So right after this pattern, these 3 lines, HL is already overwritten, so neither A nor HL are actually used after 2. Therefore, both constraints are satisfied, right? That means that we can apply the pattern and we can replace this with this, right? So we will remove these 3 lines of code and we will replace with these 2 lines of code, right? And notice that this actually is equivalent and is shorter and faster, right? So this is how the pattern-based optimizer works. It's just having a collection of these patterns that encapsulate different types of optimizations. And MDL, the only thing it does, it loads the code and it goes through the whole source code trying to apply pattern after pattern, trying to check if the constraints are satisfied, and if they are, then triggering the replacement, right? And that's basically how it works. So what I'm going to do now is I'm going to show you the collection of patterns that MDL has, and then a few more details of that, and then we'll see an example. All right, so I have here the folder with the source code of MDL. So I just wanted to show you, as I was saying, the set of patterns. So MDL has lots of different patterns. So there's different sets of patterns, but I'm just going to show you the basic set of patterns. So as you can see here, there's actually quite a lot of patterns, right? So it is not 2, 3, 4 patterns. It's actually lots of them, right? So we can actually check. There is actually 125 patterns, right? Currently in the database. So some of them are actually very simple. Like, let's see. For example, so this one is one of the simplest patterns, right? So if we have CP0, we can always replace that with OR A, right? And there's no constraints. If we have CP1, we can replace it by vec A as long as the register A is not used afterwards, right? So these are simple patterns, but some of them are actually more complicated, right? Like, for example, you can see this one has a lot of constraints, right? This one, what does this one do? Right, so this one says that if we do, so this one would be, let me just put an example here. So if we have something like pop DE and then LD like this and like this, right? So if we have something like this, if neither DE or HL are used afterwards, right, we can replace all of these by directly just pop HL, right? So this is what this pattern says. Patterns can be a bit more complex than that. Let me show you a few other examples. Let's see some interesting one. Right, so for example, this one. So in addition to just lines, we could have some wildcards. So for example, this one says, if we assign a value to a register, right, some constant value to a register, then there is some assembler code here. There can be 1, 2, 3, 10, 1 million instructions in the middle, right? But as long as this code does not modify this register, if we assign the value again, then actually this line is redundant because we had already assigned this value to the register, right? And it has not changed, so why do we need to assign it again, right? So if we have this, we can replace it with this, right? Basically, we can remove this useless statement. So this is another example of a pattern using this wildcard. Let me see. Let me go down because there's a few more interesting ones below. Where is the one? Oh, right. For example, this one. So here it says if we load a value into, so this one says something like this. If we have something like LD x ix comma a, and then inc ix, inc, whoops, ix, inc ix, right? Repeated a few times, right? We can replace this. Oh, actually, no. So this pattern says that we only have it once. We can replace this by, instead of doing it like this, we can first increment a and then load it into ix, right? And the pattern above, this pattern right here, is for the more general case where we actually have a few of these inc x, and then it says replace it with at a comma 3, because there is 3 increments, right? So if we have, this is a repetition pattern. So if we have this instruction repeated const times, right, we're going to add a to that const, right? So there was 3 times the instruction, so we add a 3, right? So we can also have this type of pattern, right? So we can have a fairly expressive type of patterns. The constraints right now, MDL supports this type of constraints, like that the registers are not used, that the registers are not modified, or they're not used in a particular instruction. We can also check the flags, that some particular flag is not used or not modified, that some expression is equal to another or not equal, that the value of a variable is within a predefined set of variables, values. Check that a register is actually a register pair, like HL is made out of H and L, right? We can check that some label is reachable with a JR instruction, right? So it is actually closer than 128 bytes. We can also check if in a block of instructions there is the same number of pushes than pops, right? To make sure the stack is unmodified and things like that, right? So we can define a collection of these constraints. So these are the set of patterns. The set of patterns in this basic pattern definition file are those that always both improve either size or speed, but they never actually increase size or increase time, right? And there's a collection of patterns, like for example this one. These patterns, these are PO patterns size. So these patterns here decrease size, but they can potentially make the program slower, right? Like for example, replacing JP by JR, right? This will reduce 1 byte for every pattern application, but it might make the program slower, right? And there's a collection of other patterns that will reduce space, but potentially making the program slower. And there's the same thing, there's a collection of patterns that increase speed, but potentially making the program bigger, right? I don't know what it can modify. So let me just undo all of my modifications. There you go. All right. So the other thing that I wanted to show is in order to check that the flags are not modified, the registers are not modified, right? So how does MDL do this? So MDL actually incorporates a file with the definition of the whole instruction set of the Z80 processor, right? So we have here all the instructions, all the DEC, INC, EX, LD, all the possible instructions that the Z80 accepts. And for every instruction, we have a collection of pieces of information, right? We have how much space does it, no, how many T states in the case of an MSX does this instruction take to execute, the number of bytes that it take, and then we have the input registers, the input flags, right? So for every instruction, we have the input registers, input flags, input ports, the input memory addresses, and also the output registers, output flags, output ports, and the output memory addresses, right? So we have a specification of what every instruction in assembler actually modifies and requires, right? These are input and output dependencies, so that MDL can actually do those checks and ensure that all the optimizations are actually safe. And whenever MDL cannot verify a constraint, then the optimization will not be applied. So for example, if there is something like this, LDA, 1, right? And then the next line says LDA, 2, right? MDL will say that this is useless and it will remove it. But if we have LDA, 1 and then red, since MDL doesn't know where is this red going to go, right? It cannot keep checking. It cannot keep checking for dependencies, so it is unsure if A is actually used or not. So whenever it encounters a red, sometimes it can tell what is the next instruction, but most of the times it cannot tell where is the code going to jump after a red. So that means that MDL is not sure, so any optimization here will not be done, and this LDA, 1 is not going to be removed, right? So MDL always plays safe. And these dependencies, I generated them by hand by reading the Z80 user manual, and then a few. It was pointed out to me in the msx.org forums that some instructions in the Z80 user manual are wrong, and they're corrected in the Z80 undocumented document. So I corrected some of those from there, but I created these by hand. So there might be mistakes. I might have made some mistake while creating this file because I created it manually. So if you use MDL and it generates an optimization that it shouldn't, let me know, because probably there's some missing dependency or extra dependency here that I should add or remove, right? All right, so I think this should be enough for now to give you an idea of how do the dependencies work. So let me just show you one more thing. And the final thing I wanted to show you is, as I showed you just a minute ago, there's different set of pattern files in MDL, right? So I'm here again in the Spelunker folder, right? So if I just do java-jar java MDL, and I optimize Splunker main doesn't right. So if I do this, I'm calling MDL with the default set of patterns, right? The default set of patterns are only those patterns that reduce both size and speed, right? So the optimizations we always want to make. However, some people might want to prioritize speed versus size, or size versus speed, right? So let me just show you how to change that. So with the default patterns, we saved 49 bytes, right? But if instead of PO, I say PO size, now I just chose the set of size optimization patterns. And instead of 49 bytes, you can see that there's a very long list of optimizations, right, that's being printed now. Every line that is printed is on optimization. So it actually managed to save 542 bytes. So this is significant. And what actually happened here is that there is a lot of JPs that can be changed by JRs. And when I coded Spelunker, I didn't do that. So there is actually full 500 bytes that I could have gained back from this cartridge. Right? This is a 32 kilobyte cartridge. And Spelunker doesn't have anything complicated running while the game is running, so it is not limited by speed in any means, right? So I could have perfectly saved these 542 bytes. And I wish I had had MDL when I coded Spelunker, because there's actually 2 items that were left out of Spelunker because I didn't have space for them, right? But with 500 bytes, at least one of them, if not both of them, could have made it into the game, right? So I'm not going to go back to Spelunker and create a new version now with those 2 items that I left out. But if I would have had it back in the day, right, I could have done maybe a better game, right? And that is the goal of MDL. Try to help you optimize better your code so that you can fit more things into the cartridge, make things go a bit faster, right? So you can, if you use run -po, you run the default set of patterns. -po size, it runs the size patterns. -po speed runs the speed patterns. And you can even create your own pattern optimization file. So you can just say PO patterns, and here write a file name with whatever file in which you define your own patterns, and then MDL is gonna use those patterns to optimize, right? So you can create your own set of patterns if you want, that maybe are targeted to your particular tool or game, right? So it is flexible on that respect. So that's basically it. I hope with that you get a good intuition of what is MDL. So I just want to say a few words about what is next. So of course, my next immediate task is to keep improving the pattern-based optimizer. Right now it works fairly well, but there's a lot of things that can be done with it, right? I want to add many more patterns. Every time I look at some new piece of source code, I realize that there's one or another pattern that I can add. I don't want to have too many patterns, because the more patterns, the slower it gets, right? Because it has to check all the patterns. So it currently has about 120, 130 patterns. But I think 150 or 200 patterns, that would be a good number, right? So maybe a bit less than double of what it has right now. And maybe I would be happy with that. After I'm done with that, I would like to work on the other 2 optimizers, the register allocation optimizer. For example, I think this would be great to optimize the use of IX and IY. IX and IY are very comfortable registers to use when coding for Z80, because they're very useful to address structures, right, with predefined offset. However, they're very slow, right? So most of the times when you use IX or IY, there is most of the times a faster way to do it with HL. That is maybe a little bit more annoying to code, but it is faster, right? So I wanted to write some specific optimization techniques to try to find better ways to code. If you have a piece of code that abuses IX and IY, to turn it into the same equivalent code by using HL, right? That would be one example, right? Another example is just optimizing the usage of the other registers. The search-based optimizer is the idea of if you specify what do you want your program to do, right? I want my program to do a multiplication, right? The idea is to search through the whole space of possible sequences of instructions, trying to find the shortest sequence of instructions that achieves the goal, right? There was a project called the Super Optimizer many years ago. I forget now who created it. I should have checked before recording this video, that attempted to do this, but of course, going through the whole search space of possible sequences is very slow, so I don't think it could generate programs longer than 5, 6, or 7, or maybe up to 8 instructions long, right? So my idea is a bit different, is given a function in assembler, search the space of modifications of that function that still maintain the same functionality, right? Given all the infrastructure that MDL already has to check all of the dependencies and input and output dependencies of instructions, right? I think this would not be very hard to do. So that's the final optimizer I would like to implement. And then we'll see from there, right? Then the other things I want to do is, currently MDL supports, I think, 7 dialects, right? 7 different assemblers. And I showed you those Z80 instruction definition file with all of the timing and size and dependencies. So currently I have 3 such files. One for the MSX version of the Z80, right? Where the time is measured in T states and there's all of those wait states. I have another file for when the Z80 is used, let's say in a Spectrum or in some other computer where the time is also measured in T states, but there's no, but where you don't have the wait states that you have in an MSX. And I also have one definition file for the Amstrad CPC, where time is not measured in T states, but typically people measure it either in NOPS or in, is it nanoseconds? I think it's nanoseconds. I might be wrong, but I think it's nanoseconds. So I support currently these 3 platforms, so you can specify whether you want to use MSX, regular Z80, or CPC with the -CPU command line argument. But I would like to support more. And also, I would like to integrate MDL better into the different development environments that people use, right? For example, I usually use shell scripts to compile my games. I just create a little shell script that I run from the command line. I don't like using external tools like make or and or libraries, or I hate dependencies. So I usually do everything myself very simply with just shell scripts and nothing else. But some people use fancy tool chains with make files and things like that, right? So I would like to find better ways or good ways to integrate MDL into those tool chains so that it's actually easy to use. And again, just a reminder, MDL is open source. You can just find it in GitHub. The URL is just in the bottom of the screen right there. And I will also put a link in the video description. So yeah, that's it. I think this is the end of the 3rd video in MDL. And I think I explained everything I wanted to explain. So if you have any questions, by all means, let me know. There's a long forum thread in msx.org where I keep posting updates. So if you're interested, by all means, drop by there. So yeah, thanks. See you.